My name is Andras Palyi. I'm working at Budapest University of Technology and Economics in Hungary. First of all, I'd like to thank the organizers for the opportunity to give this talk here. So actually, I'm going to give two talks after each other. The first one has the title Topological Insulators in One Dimension, and the second talk has the title Topological Insulators in Two Dimensions. So it's a fairly straightforward division between the topics. I do understand that maybe in this community it would be also interesting to talk about topological insulators in 3D. That's not going to happen today. This is going to be more like an introductory a lecture type talk, both of them. So we have been lecturing with two colleagues, János Asbót and László Oroszlány in Budapest about this subject. We also wrote up the lecture notes, so these are published, but also you can find them online on archive. So if you're interested in more details compared to what I'm telling you, then please refer to that publication. And then the first talk is going to be separated to two parts. So in the first part, I will introduce a one-dimensional system, a very, very simple one-dimensional system, which is called the Su-Schrieffer-Heeger model. And I will try to use this system to give you an introduction to topological insulators. By this I mean I will try to illustrate some generic concepts which appear in the theory or in the experiments also of topological insulators, including edge states, topological invariants characterizing the bulk band structure, bulk boundary correspondence, giving you a relation between the two. So this will be the first part. Using this very simple one-dimensional tight binding model, non-interacting tight binding model. And then in the second part of the talk, I would like to reflect on the fact that nowadays one-dimensional topological superconductors seem to be quite interesting because there might be some applications of them in quantum information processing. So what I mean is that one-dimensional topological superconductors are thought to have degenerate ground states, and that's something useful if you want to do noise-resistant quantum computing. And in the second part of the talk, I will move into that direction, but I will not touch superconductivity. So I will keep myself in a non-interacting system, in simple tight binding that is in this, but like this. But even in this very simple framework, I can demonstrate some features of topological protection of quantum bits. So that's I'm trying to illustrate with a very simple example there. So why do we think that symmetry topology protects certain quantum states from noise? This is going to be the second part of the first lecture. Okay, and for the second part, this is actually sort of original research, which is not yet published, but this is done together also with Péter Boros and Gábor Széchenyi, who are talented young colleagues back in Budapest. Okay, so let's start with the first part, with the introduction to topological insulators. So that's essentially that's chapter 1 of these lecture notes. Let's get started. So the first message I want to convey is the following. If the bulk has non-trivial topology, then the edge has disorder-resistant bound states. So this is now one claim or one sentence, but I haven't explained any of the concepts in it. So the first task is to explain, try to illustrate the concepts appearing in this claim, and then I hope you will understand what I mean by this. Also, these kind of claims are often called bulk boundary correspondence. So it appears in various dimensions in various materials. I'm going to show you the simplest example where this bulk boundary correspondence comes about. So if the bulk has non-trivial topology, then the edge has disorder-resistant bound states. So let's come up with a very simple model to illustrate this. That's going to be the Su-Schrieffer-Heeger model. That's a model for an actual material, polyacetylene. I won't talk too much about polyacetylene, but I want to use this toy model for the electrons in polyacetylene to illustrate the concept of topological insulators. So polyacetylene is this molecule shown here. So the black balls are carbon atoms and the white balls are hydrogen atoms. And when we model this, then you have this sp2 hybridization for the bonds, which give you these 3 bonds for a single carbon atom. And then there's a 4th valence electron for the carbon, which can move around along this chain. And so in the tight binding model which I'm proposing, which I'm showing you, this single electron per carbon atom, which is moving along the chain, that's the subject of the model. So it's an electronic model, a tight binding model. These pz electrons are moving along the chain. I forget about the hydrogen atoms for this model. So this toy model, which is called Su-Schrieffer-Heeger model, is visualized as this one. So what you see here is that you have sites. You have the gray sites and the white sites, and these sites are connected by nearest neighbor hopping terms. So the thick line is called the V, so that's a stronger hopping, a larger hopping amplitude between these two sites, and this W, that's the thinner line, that's a smaller hopping amplitude here. So you have an alternating, a staggered hopping, a stronger, a weaker, stronger, weaker, stronger, and weaker. So all of these atoms are carbon atoms. Nevertheless, because of a feature which is called Peyer's distortion, you have this strange alternating pattern of the bonding, stronger, weaker, stronger, weaker. Thereby, if you want to describe this with terms of Bloch's theory for electrons, then you have to define a unit cell which has two atoms. These two atoms are not equivalent, so this is your unit cell. You have a gray atom, which is often called A sublattice, and you have the white atom, it's often called B sublattice. So you have two sublattices. In a single unit cell, you have two sites, and thereby two orbitals. Also, I will call this lattice constant, so the size of a unit cell, A, and actually I will typically use this A as the unit of length, or also 1 over A as the unit of wave number. So often you will see just a K wave number instead of K times A. That means I take A as the unit of length. Okay, and so if I want to write up the tie-binding Hamiltonian, this is how it looks like. So this is what we call the real space tie-binding Hamiltonian. So it has two sums. The first sum is the intra-cell hopping. So if I look at my unit cell, I can have hopping between A and B sides, gray and white sides, and the hopping amplitude is V. And so that's encoded in this first sum, right? So I'm summing up for all my unit cells. So M is the index for the unit cell. I have a chain of length of n unit cells. And then within the unit cells, so M here and M there, within the unit cell, I can jump between A and B. So that's given by my first term in the Hamiltonian. The second term is the inter-cell hopping, when I jump from, let's say, this site here in the mth unit cell to this A site in the m+1 unit cell. So that's encoded in this simple Hamiltonian, where you see m+1 is meeting here, so that's an inter-cell hopping, and also A and B are the two sites between which I can hop. Okay, so this is a very simple Hamiltonian. If I want to illustrate it more, I can just write out the full Hamiltonian matrix for a chain which has a length of 4. So that's an A by A matrix, of course, and then this is the pattern. You have V hopping, W hopping, V hopping, W hopping, and so on. Very simple textbook thing. Okay, so this is the Su-Schrieffer-Heeger model for polyacetylene. And now let's see how topology enters the game, even in this very simple model. So here, the key point I want to make is that the K-space Hamiltonian maps the unit circle to the complex plane. So this is the key claim, and again I try to illustrate it with this example. So this is the real space Hamiltonian. I was showing this before in the previous slide. So this is the real space Hamiltonian, and we know from Bloch's theory that actually when we care about the energy bands in this solid, then we have to Fourier transform this Hamiltonian and get a K-space Hamiltonian. And if you use such tie-binding models, then the K-space Hamiltonian, or also it's also called momentum space Hamiltonian, is going to be a 2 by 2 matrix because you have 2 orbitals per unit cell. So this is your 2 by 2 matrix. On the diagonal it has zeros, and that's clear because there was no on-site energy term in the Hamiltonian, and on-site energy terms would appear here. So that means that the on-site energy of the A sublattice is the same as the on-site energy of the B sublattice, and that makes these two diagonal elements 0. If you do the Fourier transform for these two sums as well, then this is what you end up with. So you have an off-diagonal element, which is finite. Also, it's complex. So you see that V, this was an intra-cell hopping, thereby for the Fourier component there is no K dependence. And the other term coming from the inter-cell hopping, you do have a K dependence in this form. And of course, this bottom left matrix element must be the complex conjugate, so there's a typo you can figure out. Okay, so there's a typo here because this should be e to the plus ik. This should be the complex conjugate of the top right. Sorry about that. Okay, the key point is that you have a 2 by 2 Hamiltonian. This is K dependent. And you can always expand a 2x2 Hamiltonian in terms of Pauli matrices. So you can also write up a 2x2 Hermitian matrix as a linear combination of the three Pauli matrices, sigma x, sigma y, sigma z. And so that means that I can always write up this 2x2 Hamiltonian as this scalar product, where the sigma is just the vector of the three Pauli matrices, and this d vector is just the coefficients, which do depend on k, of course. So I can read off, if I'm trained with calculating with Pauli matrices, then I can read off directly from this matrix. Then this d vector is going to be a two-dimensional vector. It will have only x and y components, because sigma z would appear, as the diagonal term, but there's no diagonal term. So it has only x and y components, and the two vector components are simply v plus w cosine k, so the real part of this matrix element, and w sine k, which is the imaginary part of this matrix element. So this is dx up here, and this is dy down there. This is the matrix. Questions?
There the vector is x is y.
Exactly. So this is just a two-dimensional vector.
The matrix is A and B.
That's two different things. That's two different things. So in principle, I have two states in my unit cell. So I would call them A and B. But then if I allow for an arbitrary Hamiltonian, that would mean that I have also, diagonal elements. And in that case, I would need the sigma z Pauli matrix to write up this Hamiltonian in terms of Pauli matrices. So then this D vector would be three-dimensional, x, y, z. Each component multiplying, x multiplying sigma x, y sigma y, and z sigma z. But I'm lazy and I'm not writing out the third component. But these are two completely different things. I have two submatrices and I have two components here, but the reason is not one-to-one. Okay. So this is my vector. So this is nice in some sense, because this means that I have a mapping any wave numbers in my Brillouin zone to the two-dimensional plane. So you see that somehow geometry starts to kick in, and you will see also topology kicks in a while. Okay, so let me just remind you that the Brillouins...
Shouldn't this be symmetric in V and W, in the sense that you arbitrarily chose your unit cell of the short distance? You could have chosen your unit cell the other way. So there should be some symmetry here.
Indeed. So as long as you are looking at bulk properties, I think you have this freedom, and that would emerge, the symmetry would emerge in any kind of physical quantities which you calculate from these formulas. But on the other hand, when you start to look at finite size systems, then the appearance of the edge modes will depend on whether your intracell hopping is stronger or the intercell hopping is. So the symmetry is sort of lost, and I will bring an example for that. Okay, so moving towards sort of geometry or topology, we can first recognize that the Brillouin zone of a 1D crystal is actually equivalent to the unit circle, because we know that for a one-dimensional crystal, the Brillouin zone is just going from minus pi over a to pi over a. That's just this segment. And minus pi over a is equivalent to pi over a. So this is essentially, sort of topologically speaking, this is nothing else but the unit circle. Okay, so what you see here is that what this Hamiltonian shows you is that there is a mapping. It gives you an exact, specific mapping between the Brillouin zone, so the k values, and the complex plane, which is this complex number. Okay, so this is what I could call f, the f function. This is a function from the unit circle to the complex numbers. It maps k to this combination of the parameters v plus w e to the minus ik. So this is a complex valued function. Or I could also say that I have a mapping called D, which is just the same thing as this F, but it's really drawing a line in the two-dimensional space. Of course, this two-dimensional space is the same as this two-dimensional complex plane. Okay, so the F and D are completely equivalent to each other. That's just a different notation, which might be useful later on. Okay, so we have the Brillouin zone, which is a circle, and the Hamiltonian is mapping this circle to the two-dimensional plane. Okay, so let's look at some examples of band structures and also related quantities. So I just take the same Hamiltonian shown here, and first I want to understand the band structure of this model. So I diagonalize this Hamiltonian. As I said, these matrix elements I call F, and then if I want to find the eigenvalues, then this is the eigenspectrum here. So the energies, I have two of them because it's 2 by 2 matrix, plus minus the absolute value of this F complex number. So I can just plug in this complex number, and I can also evaluate this absolute value, and this is what I get. I can get some very simple formula for the dispersion relation. And now I'm plotting the dispersion relation or the band structure for a number of different parameters. So here I start with a finite inter-cell hopping, so V is 1, and I switch off I start with a finite intra-cell hopping, V is finite, but W, the inter-cell hopping, is 0. This is the first end of the spectrum, and the other end of the spectrum, I change the roles. So here, the intra-cell is 0, and the inter-cell is 0, and the intra-cell is finite, is 1. And you immediately see the symmetry, that the band structures are the same in the two cases, as they should be as long as we are looking at bulk structures. Also, what you see is that you have a flat dispersion. These are dispersionless bands. And that's because if one of the hoppings is set to 0, then the whole chain is just separating to dimers. Two atoms and two atom dimers. And then for each dimer, you have a bonding state, an anti-bonding state. And for each dimer, you have the same spectrum. And that's why you have a constant spectrum, also in real space, but also in wave number space. And then, of course, things get sort of dispersive when you change these relations. So here, both values are finite, both the intracell and intercell values are finite. And there is one sort of critical point where the value of V and W, the two hoppings, is the same. In this case, you have sort of a metallic band structure. So in the first, second, fourth, and fifth case, you see a semiconducting band structure, insulating band structure, because there's a finite gap between the lower states and the higher states, so the valence band and the conduction band in condensed matter language. So these are insulators, but this middle example, they touch, so that's sort of a metal in that sense. If I consider half filling of these band structures with electrons, then that's going to be a metal, even in that case. Okay, so what does the geometrical consideration tell us about these systems? Unfortunately, the resolution is not very good here. I apologize for that, but I try to explain what's plotted here. So what is plotted here is that I have this dx and dy axis. So dx and dy is just the same as the real part of f and the imaginary part of f. Okay, I just showed this correspondence in the previous slide. So what I'm drawing here is that I tune my k wave number. I tune it from -pi to pi, so over the Brillouin zone, and I look at how my f or d vector looks as a function of this k vector. So I should see lines, loops. I should see loops on this plane. So this plane is the dx, dy plane. And so in this very trivial case, when I have the inter-cell hopping turned off, then I have only a single point as the image of the Brillouin zone, because as you see, if w is 0, then there is no k dependence in my Hamiltonian, and I can read off that the real part of my f quantity is just v, and the imaginary part is just 0, so my loop is actually a single point in this dx dy plane. And if I do the same procedure, I do these plots for the further cases as well, then what I see is that for this non-trivial case, I do see some kind of a loop. This is actually circularly shaped. I do understand why it's circularly shaped, because I have finite v and w. My v is just giving me the displacement of the center of this loop along the dx axis, so that's here. And then I have w e to the minus ik, that's going to give me this circle with a given radius. So this is a circle shifted from the origin with its center. And it's an important observation here is that it does not go around the origin of the dx dy plane. So that's somehow where topology kicks in. So this is now a loop which does not go around this, the origin of this plane. If I move on, I look at this metallic example, then again I can figure out that v equals w, then the radius of this circle is the same as the displacement of the center from the origin, which means that this circle will exactly touch the origin. And that means that actually I do have a metal. I don't have an insulator, I don't have a semiconductor, I have a metal, because the length of any points on this circle is just encoding the energy of the state, because the energy is nothing else but the absolute value of this f, complex number, but that's the absolute value of this vector, dx dy. Okay, so having a point exactly at the origin means I have a metal there. So if I tune my parameters from left to right, then this is some kind of a critical point, a transition point where my gap is closing, and then it reopens again. And when it reopens, when w is bigger than v, then this circle is getting even bigger, in the sense that its displacement of the center is smaller than the radius, and thereby this will circulate around the origin. So this circle will, go around the origin, and also if I go further, I have the same kind of topology or geometry of this setup. So, okay, it's not clear what does it mean physically at this point, these kind of different topologies of these. But what I can say is that coming from this very simple model, I can classify these Hamiltonians by looking at these curves drawn on the dx dy plane and just classifying these curves by saying how many times they go around the origin. And in that sense, I'm distinguishing between the first two examples where this so-called winding number, so how many times do I go around the origin, is just 0. I don't go around the origin at all. And these others where I have, again, insulators, but my winding number is not 0, it's 1.
But
and,
again,
yeah.
If I want to assign any physical meaning to winding number, which I assume you want to do at some point.
Right.
The two extremes, as far as I'm concerned, are the same thing. You just chose the wrong basis. And that means winding number has no meaning. So how...
It seems so, yeah. Yeah, it seems so. So in the next slide,
okay, good.
Something about this will come up, yeah. Yeah. Exactly, so the point is that, of course, if you are in the bulk, you will never see any consequences of these different noise differences. That's absolutely true, yeah. Nevertheless, let me spend one more time on this bulk thing. So I'm just saying that by this very abstract, non-physical mathematical construction, I can nevertheless sort of set up a phase diagram for the Su-Schrieffer-Heeger model. I have two control parameters, V and W, the two hoppings, and what I was showing is that depending on the relative strength of the two hoppings, I can have either a 0 winding number, and I can give it a label 0. I can also give it a label trivial. And also the other phase, I can give it a label 1 or give it a name topological, but it's not clear what it means at this point. Okay, and then one phrase which often pops up when people talk about topological insulators is this adiabatic connection. And by this, people usually mean that if you talk about non-interacting band structures, then what they mean is that two different models can be adiabatically connected to each other if you can continuously deform the Hamiltonian from one to the other without closing the gap. So that's what people mean by adiabatic or continuous deformation in the context of topological insulators. Can you go from one to the other without closing the gap? And that's, you see that this is sort of makes sense on this abstract level because indeed, now we can say that these two guys are adiabatically connected because I can go from one to the other continuously without closing the gap. But these two guys, I cannot deform continuously to these two guys because I have to go through this point where I close the gap. Okay, so this is somehow the meaning of adiabatic connection. And now, where am I? So I promised to bring this conclusion that if the bulk has non-trivial topology, then the H has disorder resistant bound states. So I have so far argued that in an artificial mathematical sense, I can assign some topology. I can call a SSH model trivial or topological, depending on this winding number. So I can assign a topological label to different pieces of the same model. And let's see what I mean by edge states. So the physics of edge states is very clear in a very well-defined limit of this SSH model. So my point I want to make on this slide is that zero intracell hopping implies zero energy states at the edges. Okay, and to illustrate this, I take the so-called fully dimerized limits of the SSH Hamiltonian, and I take finite samples. I want to talk about edges, so I have to take a finite sample. So I take this example. This is now, I think, 10 unit cells. So I have 20 atoms, 20 size. My Hamiltonian is a 20 by 20 matrix in real space. Of course, in Fourier space, if I would look at the bulk, it would be a 2 by 2 as before. And now this is the fully dimerized limit, which is called trivial. So this is when I have V equals 1 and W equals 0. That means that only the intracell hoppings are finite, and the intercell hoppings are 0. So as I said before, in this situation, the chain is separating to individual dimers, and thereby you have a large amount of degeneracy, a tenfold degeneracy of all the states. And this energy spectrum is illustrated here. So this is the sort of trivial, fully dimerized case. If V is taken to be 1, then actually the bonding and antibonding energies are just -1 and +1, and I have 10 identical copies of all of them. So this is the energy spectrum of this setup. On the other hand, if I go to the other limit, which I was calling topological for no reason beforehand, that means I set this intracell hopping to 0 and I set the intercell hopping to 1, then this is what I have. Again, the chain is separating into dimers almost everywhere, because you have these dimers. I'm circling the unit cells, but these dimers are, inter-unit cell objects, but nevertheless, these are just the same dimers as before. I have 9 of them. So again, I have 9 identical bonding, antibonding states. So I will have, in the spectrum, I will have a 9-fold degenerate level at 1 and a 9-fold degenerate level at -1. But you see that in this setup, there are sort of lonely sides on the left edge and also one on the right edge. They are not coupled to anywhere. They have 0 on-site energy, so they're going to live at 0 energy. So in this setup, if I consider a finite size setup, then it starts to matter whether my intracell or intercell hopping is finite. And in this situation, this topological fully dimerized limit, when my intercell hopping is finite, then I have these 2 degenerate states. One is localized here, and one is localized there. Okay, so this is where sort of topology starts to get some meaning for this finite sized setup.
But I get the same thing if I shift the top one by half a unit cell, right?
Absolutely.
Okay,
Absolutely.
fine. So
yes.
It's just whether you're having full unit cells or not unit cells.
It's related to, yeah, you can phrase it like that as well.
Okay.
Yes. Now I come to the, okay, so we now see that we have edge states in a very specific limits. So very simple limits. The question is, do these edge states survive if I introduce, if I go away from that limit, or even if I introduce some kind of disorder? So do they survive? And by surviving, I mean, do they remain localized? So that's one thing. Do they remain localized? But the more important thing is that, do they remain at 0 energy? Because if I'm thinking in terms of quantum bits, then I don't like if my quantum bit energies are, shaking. I like when they are very much fixed. So that's the more relevant question, I think. Are these edge states robust in terms of the wave function localization, and are they robust in terms of the energy robustness against the fluctuations of something in the Hamiltonian? Okay, and to go to this direction, one thing I need to introduce is a symmetry, sort of a generalized symmetry. So it's not like a symmetry you are used to rotations and mirror symmetries and so on. So you're used to these conventional symmetries in quantum mechanical physics, but chiral symmetries is something different. And the point I want to make is that SSH Hamiltonians have this special chiral symmetry, and that gives you a fairly robust behavior of these edge states. So let's see. Let me start with a definition. A gamma local unitary operator is called a chiral symmetry if it maps the Hamiltonian to minus itself. So usual symmetry is mapping a Hamiltonian to itself. But this is not now a strange symmetry in the sense that this is an operation, this is a unitary operation and local, which is mapping the Hamiltonian to minus itself. Let's go to the example just to appreciate what it means. So as I was showing you, the n equals 4, so 4-unit cell SSH model has this very simple Hamiltonian with nearest neighbor hoppings, VW, VW, and so on. And it's very simple to check that this 8x8 matrix, where you have only diagonals 1, minus 1, 1, minus 1, 1, minus 1, 1, minus 1, this is actually a chiral symmetry of this Hamiltonian. Okay, so if you could just do the matrix calculations, you can plug in gamma here, h here, gamma dagger here, and you find that it's going to get minus h in the end. And this is sort of I'm not saying that this is a generic feature of polyacetylene or any physical systems. I'm saying that this is a feature of this particular model, but I'm using this model to illustrate certain consequences of symmetries or generalized symmetries, and that's why I'm bringing this up, not because I think it has some actual physical relevance in real materials. But the point is that there is this chiral symmetry, and that is a reason for having only nearest neighbor hoppings and not having any on-site energies. So if I introduce different on-site energies on the A and B sublattice, then I would break this chiral symmetry. Also, if I would introduce next nearest neighbor hoppings, like making this 0 finite, I would break this chiral symmetry. So it's a very specific thing. Nevertheless, this is a symmetry of this model. This equation is fulfilled with these Hamiltonians. And now if you have a chiral symmetry, then it has a few interesting consequences. So the one consequence, which probably most of you are familiar with from superconductivity, is the up-down symmetric energy spectrum. So if I have an eigenstate at energy E, and I have chiral symmetry, then these two things imply that my chiral pair, so gamma times my original state, is going to be also an energy eigenstate, and it's going to have an energy minus E. So it's an up-down symmetry of the spectrum. And I think all of you who are familiar with the Bogusla-de Gennes formalism of superconductivity, this up-down symmetry is very familiar because this you also have there. So there it's not the consequence of chiral symmetry. So there is the consequence of something else. It's called the particle symmetry. Nevertheless, it's there. It's very similar to, so the effect of it is similar to the effect of chiral symmetry. It's not identical, but it's similar. So as in Bogusla-de Gennes theory, here you also have, because of the chiral symmetry, you also have this up-down symmetry of the energy spectrum. Maybe I should note here that if you go to the Bogusla-de Gennes description, then this particle Hall symmetry